Hello everyone, welcome to Module 6 for Data 609, Mathematical Modeling Techniques for Data Analytics course. So in this module, we're going to discuss a couple of key concepts. One of them is clustering. Second major topic would be decision trees and random forest. And the third topic would be mainly on Bayesian classifiers. Okay, before we start, let's take a look at why we're studying this and what is classification and clustering. So data mining methods include many different techniques such as clustering and classification, and feature selection and machine learning techniques. In terms of data, there are structured data with fixed structure, including numeric data that we exposed previously, and unstructured data. It can be text, can be social media images or web pages or business transactions. It can be mixed of structured and unstructured data. And in terms of big data, what is big data? Big data actually is famous for 3 V's, which would be volume, velocity, and variety. But here we actually introduce 5 V's, which is more comprehensive and complete comparing to 3 V's. And you probably already know volume in terms of the data size, it has been dramatically increased. And velocity, the rate of data accumulation, has been really fast and increased quite a bit in the past 20 years. And then variety, the variety of the data, different types of data, as we just discussed, structured data and unstructured data. Value, the purpose of the analysis is to extract useful feature and gain insight, that is to make sense of data. And veracity, veracity is the quality and accuracy of the solutions, and in other words, it's uncertainty of the data. So that's 5 V's for big data: volume, velocity, variety, value, and veracity. Before we discuss clustering and classification, we want to introduce distance metric. So let's take a look at these 2 vectors. The first vector is x, second vector is y, and then the condition distance between those 2 vectors, dxy, is defined as LP norm distance, which is x minus 1 absolute value Cartesian LP norm of p, which essentially is xi minus yi powered by absolute value powered by p, and then summation of all of the difference in the vector, and then powered by 1 over p. In case of p equal to 2, it is the standard Euclidean or Cartesian distance. And the Manhattan distance is essentially L1 norm, which is using the p being 1 in the LP norm function. That's Manhattan distance. So the reason that we need to introduce this distance metric is just because how do you measure how far away or how similar to data set or to different data observations in your data set? That's why we need to introduce this distance. And then as you can imagine, for different algorithms, potentially, or for different data set, and for different algorithm, for different data set, you might be using different distance metric. And which metric would be the proper one is something that you should try it out in your data set. The other distance metric, for example, Jacob similarity. What it does is it's For two sets U and V, it is the intersection of U and V divided by the union of U and V in terms of the size, right? Absolute value, the size of the interaction between U and V, and the size of those two set union. And then the distance, JCAT distance, is defined as 1 minus J UV, which is d UV. Next distance metric is edit distance. We want to see that the distance between U and V, those two string text, I would rather say, and then how many number of insertions and deletion of a single character that we'll need to convert U and V. For example, from ABCDE to ACKDEG, what you would do is you can delete B from here, and then you got the AC, and then insert a K in here. And after that, you got ACKDE, and then you add a G at the end. So that would be 3 operations. So by deleting B, inserting K after C, and then insert G after E, string U can be converted to string V. So that would be added distance between those two strings would be 3. Hamming distance. Hamming distance is the number of components which two vectors or strings differ. For example, these two, the difference between those two is 3. Let's say the second one is different, the third one is the same, the fourth one is different, and the fifth one is different. That's why it's called the Hamming distance between those two is 3. There's some other distance as well, right? It's called fuzzy distance, fuzzy relationships, and depending on the context and the applications, time can also be considered as distance. Even for the same data set and same algorithm, different distance metrics used for analysis may lead to very different results. That's just something you should be aware, and you should be picking the proper distance metric for your analysis. And the majority of the time in algorithm or packages, there will be some recommended distance that you should be using. Let's take a look at clustering. So what is clustering? Clustering is trying to divide a set of n observations into some clusters. For example, k-different clusters, so as to minimize certain clustering measures or objectives. So you should be aware that for clustering, there is no label for your data. In other words, there is no dependent variable. You do not know which point belongs to which type of cluster. Now, the first example that we want to discuss is hierarchical clustering. Hierarchical clustering usually works well for small data set. What it does is it starts with every point in its own cluster. So if you have n data points, then we start with n clusters and followed by a simple iterative procedure. So let's look at the algorithm itself. Each point belongs to its own cluster so that we have n clusters. And for all the data points, choose 2 nearest clusters to merge into one cluster. So essentially, for all the data points for the first iteration, it will have n clusters and then combine the nearest 2 into 1 so that you can reduce it to the dimensions. Reduce the dimension so that initially it becomes n minus 1 for the first iteration. And then you can update k minus 1 to k, repeat until the metric measure goes up. So essentially, continue with a combination of the cluster. So at the end, you say, okay, I stop somewhere, right? In other words, you have to predefine how many clusters in your data set. Assume you have 300 data points, you're kind of thinking that you probably have 5 clusters. You would do this process iteratively until your data shows 5 clusters. Complexity of the algorithm is O big O n powered by 3, where is the number of points. For 1 billion data points, this can lead to 10 powered by 27 floating point operations, which can be very computationally expensive. As I just mentioned, right, if you have 300 data points, in order to reduce to fast 5 clusters, it does take quite a bit of time to run the algorithm. So that's hierarchical clustering. Let's look at k nearest neighbor. K nearest neighbor is an algorithm that is called a voting algorithm. It uses k sample data points in terms of given distance metric to determine the class of the data points under consideration. Here is an algorithm. Before we actually go to the algorithm, let's take a look at this example on the left-hand side. The main idea of this classification is to say that assuming that the data has 2 classes. One is a star. Let me get a pen here. One is a star. The second type is this diamond. And then I have the task is to determine what class this spade, green spade, belong. If we use k equal to 3, nearest neighbor, which essentially this is this blue circle, what we see is if we only look at nearest neighbor of those 3 to see which one this should belong to, you see that there will be 2 stars, 2 diamond and 1 star. You would think that this green spade should be diamond. If we're using a bigger circle like this black line, then what we have is 4 stars and 3 diamond. Then we think this one would be star. However, if we use this line, red line in the middle, you find that it would be 3 stars and 3 diamond becomes a tie. So you would not know what this green spade belong to. So let's look at the k's nearest neighbor. First of all, you define a k. K could be, in the example, could be 3, could be 7, could be 6. So you define that first, and then compute the distance from other points to this I, and then sort the computed distances and select k points with smallest distance, and then assign the test point to the class by the simple majority. So that's the algorithm itself. So here you should be aware, this shows the importance of choosing the right parameter k and its sensitivity to the parameter of k. So in general, k should be odd number. Typically, k should be less than square root of n number of data points. So that's k's nearest neighbor algorithm. Moving along, let's look at Kmeans clustering. Kmeans clustering method is to divide a set of n observations into k different clusters so that each point x belongs to the nearest cluster Sg with the shortest distance. you can see here, suppose that each one of the clusters mean is in somewhere here, C1, C2, and C3. What we're trying to do is trying to minimize xi minus Cj of all the clusters L2 norm. And then we're trying to minimize that distance. It's trying to divide the n data points into k clusters. So what it does is it defines a k, choose randomly k points as the initial centroid of k clustering. And the example that we just have, right? If we have 3 clusters, then we randomly select k points, and then assign for each remaining point I, do assign I to the cluster with the closest centroid and update the centroid of that cluster. So let's use this as an example. Let me get a pen. So assume that we started. Let me use a different color here. Maybe pick orange. So suppose that we select a centroid. We select this one first as our centroid. This one, second one. It should be different color though, right? The third one. So what would we do? What we do is we try to assign based on distance after our initial selection of the centroid. Hold on. So after assignment, what would happen, right? Assume that this looks like closer to that circle, right? This distance, these points probably would belong to the second cluster. And then you can see that these points would probably belong to the, let me do it with a better way. This probably would belong to this cluster. And of course, many of this probably should go to the first cluster. So now you have 3 clusters. You probably would be wondering what do you do with those, because what I'm drawing is not perfect, but they should belong to somewhere, because based on the distance from here to this distance versus here to this point, then this should be really belonging to this general area. And then after you do this, what you do is you compute your centroid of all of these data points. Compute your new centroid. Then it's no longer this orange. Potentially you could go where? Let me use a square, right? This time. You probably can go somewhere here. This probably goes somewhere here, right? So now that's the second step. If we go back to the notes, right? What we do is we assign and then update the centroid and then recompute. Next thing that we want to recompute would be what's the distance among all the nodes to this centroid, and make a decision on what this boundary should look like. It would be something a little bit different from this first try. And then continue to update. Calculate the distance, find the centroid, calculate the distance assigned to a specific cluster, and the third step would be compute the centroid, update its centroid, and then the next thing you want to do is just repeat. So that's K-means clustering. Just some issues that you should be aware. Initialization of K clusters may not be efficient. In order to avoid problems, usually you want to choose the initial points are far from each other as possible, as much as possible. And then the results sometimes are not good. Random start may be needed to avoid too much dependence on the initial points. And then in terms of complexity, it's quite expensive. That's why it's not suitable for big data. Just be aware that all major packages for data mining have implemented case nearest neighbor and K-means methods. We can do some testing on our own. Okay, this is K-means clustering. Remember that we discussed hierarchical clustering, case nearest neighbor, and K-means clustering. Just be aware that case nearest neighbor is a classification algorithm, but the other two are clustering algorithm. Okay, I'll stop here and we'll continue our discussion next time. Thank you.